Turn to this. Good, thank you. So today is April 13th, and the situation is the following. Last time we did lab 3 and we started the electromagnetic induction. Then we have a spring break, and today we will continue with electromagnetic induction. As a reminder, the second exam is the day after tomorrow from 9:40 to 11:40. Chapters 20 and 21 and labs 1 and 2. Okay, lab number 3 is going to be due on the 22nd of April. So let's continue with what you have to know about. We covered, right, extensively in a qualitative way. What is electromagnetic induction? Today is 2026. And now I'm going to get in the nitty-gritty details of electromagnetic induction. What I want to do, I want to lay down here the sections of chapter 22. Okay. And let's take a look at the book as well. So we are Twenty-two. Here you go. That's the chapter 22 of the book. He's illustrating how we can induce a current in a solenoid, in a coil. So we have a tube around which we wound a circuit. We wind this circuit several loops, right? And the circuit is connected to an ammeter. It has no battery whatsoever, this coil. This coil has no battery whatsoever. When we approach a bar magnet, back and forth, we are changing the magnetic flux inside this coil. We end up inducing a current, okay? Either a positive current or a negative current, either the current flowing one direction or the other direction. This is a well-known effect that is spelled out in a law of physics. And that's what 22.1 is all about. Okay. And here's an application of induced electromotive force in the cruise control. Okay, the cruise control of our car, we can use electromotive, the induced current in this device. There are all sorts of applications, by the way. That's just one of them. It's just one of the applications of electromotive force, of induced electromotive force. Here's another example. Okay, we have a magnetic field. Okay, this magnetic field is constant. This magnetic field is constant. Okay, but and then we have this closed loop here, and what we do initially is a square, is a rectangular circuit, which is connected to my ammeter. If I pluck this wire here, make it moving back and forth, just like the strings of a guitar, what's going to happen? What's going to happen is that the area that is subjected to this magnetic field is going to change, okay? The area of this coil is going to change, okay? While the area of the coil is changing, because the area of the coil is changing, the magnetic flux is also changing. So it's not that you must have a change in magnetic field. You must have a change in the magnetic flux. If you get a change in the magnetic flux, you manage to induce a current, and that's what happens here. Okay, the area of the circuit keep increasing and decreasing. Because the area of the circuit keep increasing and decreasing, the current is going to flow back and forth, not just in one direction, but back and forth. Okay, depending on the whether the area increases or decreases. Just a reminder. Okay, and there is another way of doing the same thing. Okay, motional EMF. Motional EMF. If you get a conducting rod moving in a magnetic field, according to the magnetic force law, okay, it's like having electric charges moving in this magnetic field. So you do V cross B. Remember that? V cross B. If the charge is negative, if the charge is negative, the negative charges are going to be pulled downwards here in this rod, in this conducting rod. And we're going to have an excess of positive charges at the top. So we end up having with this electric potential difference, an accumulation of charges at the bottom, negative charges at the bottom, and accumulation of positive charges at the top. And here is another example. Here is another example, just like our current that we plucked, and the area changes. Right here, the area is also changing. So we have a wire connected to a light bulb. Okay, one terminal of the light bulb, the other terminal of the light bulb. This terminal of the light bulb is insulated from the other terminal of the light bulb. So we have a circuit. So think about that in terms of a railroad track. Think about a railroad track. And you have a magnetic field into the board. Okay? So if we have a bar, a conducting bar as well, moving to the right, like you see in this drawing, you're increasing the area of this circuit, and consequently you are increasing the magnetic flux as well. And because you're increasing the magnetic flux, the thing is not vibrating, right? It's just moving linearly. Because you're increasing the magnetic flux, the current must flow in a direction that is going to oppose the magnetic field. Do the right hand rule, right? Magnetic flux increases, the current must flow in a direction that opposes the change in the magnetic field, the change in the magnetic flux. We also covered that, right? So let's write it down, the examples, notes. Okay. We covered that. And we also covered that motional EMF, right? Different ways to induce a current. Okay, in general, you must vary the magnetic flux in a closed loop current in a closed loop, right? To induce an electric current. In general, you must vary the magnetic flux in a conducting loop, in a closed conducting loop, to induce an electric current in this loop. Okay? Ways, right? Ways to, so here you go. One way, one practical way, approach and let's see, move a magnetic bar closer and further away from a from an electric from a conducting loop, from close to and further away from a conducting loop. That's the first example that you saw there in the book, right? That, let's see. This one. Okay. Another way. Subject a conducting loop to a magnetic field and pluck one of the arms of the conducting loop. Okay, move a magnetic. In this case, the first one, in this case, you have a changing magnetic field that results in a changing magnetic flux. Okay? Subject a the second one, subject a conducting loop to a magnetic field and pluck one of the arms of the conducting loop to make it oscillate like the string of a guitar, right? As the arm of the conducting loop oscillates, comma, the area of the circuit changes in time. The area of the circuit changes in time. A as a function of t, right? This changing in area results in a changing magnetic flux, which induces a current in the circuit, in the closed loop circuit, like that. Another one. This is we can call that motional. This is a type of motional, motional induced EMF. Okay. Also, if you move a bar along a magnetic field, along a static magnetic field, according to the magnetic force law, Lorentz law, it's also called Lorentz law, negative charges should be pushed, right? Pulled in one direction, and positive charges should be pulled along the other direction, creating a charge distribution and a potential difference, right? And a potential difference like that. And you saw that example as well, which is this one right in here, okay? Conducting rod, V cross B, right? For positive charges, the positive charges accumulate at the top. For negative charges, the negative charges ending accumulating at the bottom. It's a type of induced induced current, okay, which is creating potential difference. Now, if you are going to create a current that remains in the circuit, what you have to do? You have to wire this bar. This bar is gonna behave just like a battery because of this difference in electric potential difference, okay? If you close the circuit, you end up with a current flow in the circuit. Okay, now another way for if you place the above bar in contact with a conducting rail, that's the best way of describe it. A conducting rail, right? Just think in terms of a railroad, like in a railroad, like in a railroad. Come on. By introducing a light bulb in this railroad, you will observe, you will see, right? You will see that the light bulb will light up, indicating that there is a current in the circuit, okay? This induced current results from an increase in the area of the circuit, which results in an increase of the magnetic flux. Okay? At least. Let's see if we have another example here. Here you go. Okay, so here you go. Here's the same thing that we worked on, right? That I showed to you, and let's see. And we can do some mathematical examples. Let's do some mathematical examples, okay? One more student coming in. Example. And in order to do a mathematical example, we have to, okay, that's the qualitative idea of, that is the qualitative idea of electromagnetic induction. If you want to quantify, it, the amount of current that is induced, you need to spell out a mathematical law of this effect. And I don't think I did that, right? I covered only last time. I covered only the qualitative idea. I didn't introduce you to the formulas. Let's take a look here. Yeah, I didn't introduce you to the formula. I'm going to introduce you to the formulas right now. Here, the magnetic force law. Here's Gauss's law for electricity. Here's Gauss's law for magnetism, and here's Ampere's law. But then we have one more law of electromagnetic induction, which is named after Faraday. Let's take a look here. You've got to memorize, not just memorize this equation, but also you have to know how to use it. Let's see, where is the equation right here? See here. Oh yeah, I got it. Okay. Okay, the law, Ampere's, Faraday's law. Or Faraday's law. Or Faraday's law. Which is given by, the potential, the induced potential, electric potential, the induced electric potential of the circuit can be abbreviated either by the V or by this epsilon. Okay, is equal to a minus sign here. N, what's N? N is the number of loops in your circuit. And here is the change of magnetic flux with respect to time. Okay? And the magnetic flux, you already know, right? What's the magnetic flux? Where the magnetic flux is given by the magnetic field multiplied by the area and the cosine of the angle between the magnetic field and the area vector. I'm gonna abbreviate it as theta, like that. That's what the magnetic flux is all about. Okay, so different ways of, so just by looking at this equation, you can see that we have at least 3 different ways of changing the magnetic flux, okay? 3 different ways of changing the magnetic flux in time, okay? Just by looking at the equation. The first one that I mentioned to you, we can vary the magnetic flux by varying the magnetic field, right? Everything else can be constant. One way. It is the case, this is the case of approaching This is the case of moving, okay? Of moving the magnetic bar closer and further away from our closed loop circuit. Closed loop circuit. Okay. Another example. Another example. Another example of the above case is to turn on a nearby circuit. Turn on slash turn off a nearby circuit, which will produce a current that varies in time and a magnetic field that varies in time that is associated with this current. Okay, two different ways of varying the magnetic field. Another, okay, three different ways. Let's see. Change the magnetic flux in time. Let's put here. One, by changing the magnetic field. Two, by changing the area of the circuit subjected to the magnetic field. Three, oh, and then we have one more. This is a little bit more difficult to visualize, by changing the angle that the magnetic field makes with the area vector, okay? By changing the angle that the magnetic, that the B field vector makes with the area vector. Okay, so here you go. In mathematical format, we have the following. We have the following. One, changing the magnetic field. Okay, by changing the magnetic field like that. And then the next one, by changing the area of the circuit. Okay, so the time dependence here is moved to the area of the circuit. Okay. Continue numbering. Yeah. Either by plucking, right? The arm, one arm of the circuit, plucking one of the arms of the circuit, or by moving the metallic conductor along a conducting rail. Okay, and then we have finally, we have the other one here. That's a little bit more difficult to visualize. By by changing the orientation of the circuit with respect to the magnetic field, with respect, or its area vector, with respect to the magnetic field vector. Okay, and now the time dependence here is gonna be right here, right? And that's this last example. This last example is the very basic principle of the generator, of the electrical generator. So if you want to generate electricity, all you have to do is to put, for instance, a closed loop circuit rotating in a magnetic field. Okay, to achieve that, all you have to do is to rotate a closed loop circuit inside a magnetic field. 3 different ways of inducing a current. And then you can have the combination, and then you can have a combination of every 3 too, okay? So in reality, you can 1, 2, 3, right? And then you can combine 1 with 2, 1 is 3, and 2 is 3, right? You can also achieve the same result by combining all the 3 possibilities among themselves, right? Mathematically, how would we spell that out, right? One way, provided, of course, one doesn't cancel with the other. Provided, right? Provided, of course, that one variation does not cancel the other, but it's possible, okay? It's possible. Or, here you go. You can have a simultaneous change in the magnetic field and in the area of the circuit to change the magnetic flux. You can have a simultaneous change in the magnetic flux and the orientation of the circuit with respect to the magnetic field. That's another way. You can have a simultaneous change in the orientation of the magnetic field and a change in the area of the circuit. And then you can also have, finally, the last one, everything changes at the same time, right? So we have a total 1, 2, 3, 4, 7 different ways of inducing a current in the circuit. 7 different ways of inducing a current in the circuit. And like I said, the formula, mathematical formula that you have to memorize is this one. The induced voltage is equal to the change in magnetic flux with respect to the change in time. Let's see, this one I want to, like that. Good. Make it look nice, right? Now let's do an example. Mathematical example. Okay. Example. Consider the circuit below. This example was taken out of the book. Example. Okay, here we go. And don't forget the direction of the current. This is what we call to find the direction of the current in the circuit, comma, we use Lenz's law, which states that the flow of the current in the circuit must counter the change in the magnetic flux in the circuit, like that. So we have to let's work in this example now, right? Mathematically, there is a uniform magnetic field of no intensity B pointing into the board, and a light bulb of resistance R connected to the circuit. The bar on the right is moving with velocity V. Find moving with constant velocity V, right? With constant velocity V. Find the magnitude of the induced current in terms of the other parameters. The other parameters means what? V, velocity, L, and B. V, L, and B, right? Find the magnitude of induced current, I, in terms of the other parameters, B, L, and B. Okay? Solution? Solution. Apply Ampere's law. The induced, the induced electric potential is equal, okay, to the number of loops in the circuit times the change in magnetic flux divided by the change in time. That's Ampere's law. Start with not Ampere's, Faraday's law. Faraday's law, right? The negative sign that you see here is exactly the Lenz's law that I discussed before, okay? Now, because we have electric potential induction, this electric potential induction is related to the resistance of the light bulb. And by the way, we gotta put resistance of the light bulb as well, okay? If you want to find I, the induced current IND. Okay. Oh yeah, we have resistance here. Yeah. In terms of the other parameters, V, R, L, and B. Okay, so here we go. The number of loops is just one, right? There's this circuit has just one loop. Here's the loop. We do not have multiple loops, just one. The potential, the induced electric potential can be related to the current, to the induced current and the resistance by Ohm's law, using Ohm's law. Using Ohm's law, we have resistance of the light bulb, induced electric current. Now we are going to applying the definition of magnetic flux. We get, this is the definition of magnetic flux, right? Which, by the way, can be here written in another way. Let me just copy everything here. And then I will walk you little by little. Okay, I'm gonna need more than one. We did that, right? Now we can say that the magnetic flux is going to be the magnetic field times the initial area of the circuit that we do not know, plus the increase in the area of the circuit, right? Which we are going to find shortly. In the next step, okay, that's the next step here. We still do not know what's the initial area in the circuit, but you're going to find out that we're not going to need it. But the increase in the area of the circuit is going to be what? Is going to be our, let me write that as being delta x along the horizontal direction, right? Times the width of the circuit, which I called L, right? The incremental change along this x direction times L. That's the delta area that is increased. And now in the next equation, we can rewrite it as being VT. Oops, VT. Oops, VTL. Remember, we do not know A naught, but we do know VT is a variable that's changing time. L, we know B, which is the magnetic field. Let's see how we can solve this problem. Okay, I got it only the magnetic flux, right? What about the change in magnetic flux? We need a change in magnetic flux, okay? That's what we need here. The change in magnetic flux, okay, is going to be the magnetic flux at a given instant of time and the initial magnetic flux. Okay, let's see, let's put it this way, initial magnetic flux. The initial magnetic flux is B times A naught, right? Make sense? The initial magnetic flux is exactly this term here, the first term in that equation. Okay. And the final magnetic flux is going to be what you see right in here. The magnetic field doesn't change for this specific example. And now I can rewrite it as being, let's say, can put a parenthesis here, right? And take this one out. Delta A. What you see right in here is going to be delta A, which we already calculated, right? Like that. But delta A doesn't depend on A naught. Delta A is just VTL. Let's see, not VTL, sorry, there's a mistake here, okay? Is VL delta T. We gotta put delta T, which is the amount of time that went by since the beginning, okay? So here go VL delta T. So that's what the change in the magnetic flux looks like. We didn't finish yet. Now look what happened. We know B, we know B, we know V, we know L, but we do not know delta T, and you do not need to know delta T. Why is that? Because of this equation right in here. Notice that delta flux must be divided by delta T, right? Using, here you go, using Faraday's law. Faraday's law. Here you go. Substitute right in here. Look what happens to the delta t. Although we do not know delta t, we do not need to know it because it cancels in the equation for the Faraday law. And that's what we end up getting. And by the way, I'm asking the magnitude of the current, right? Let's take a look here. Find the magnitude of the induced current. And the magnitude of the induced current, we write like that. Looks like someone has a microphone on. Here you go. Good. Let's see if I can get the bar in there. Yeah, that's the bar. Another bar. Yeah, good. So I got the bar. That's what we want. So here you go. Now recall that we want the magnitude of the current. Let's put here the bar right in here. Okay, because we want the magnitude of the current, we can cancel out the negative sign there. BV and L are positive, and we finally get that the magnitude of the induced current is BVL over R, like that. So that's how we solve this type of problem. Okay. So let's do a numeric example of the above equation. Okay. Consider the value of, let's see, the magnetic field of the Earth at the North Pole. The magnetic field of the Earth at the North Pole. Consider the value of magnetic fields. Let's say we built a railroad track instead of the North Pole. Let's put in the South Pole, right? South Pole is better because we have a huge continent there. And then we can think about building a railroad track there in Antarctica, in the South Pole. Okay, consider the value of magnetic. Let's see, practical numerical example, right? Practical numerical example. Okay, consider a railroad track built on the on the no, it should be north, right? North magnetic pole of the Earth, which is nearby the south geographic pole, Antarctica. Geographical pole in Antarctica. Antarctica. In the Antarctic continent. Let's see. Antarctic continent. Why he doesn't like it? Antarctic. Okay, that's why. Continent. Suppose that we build a railroad track there. The distance between the rails, use it as being 1 meter. 1 meter, no, it's more, right? It should be around 2 meters. And put your train, right? To drag a conducting bar along the railroad, let's say at 40 kilometers an hour. Let's use 40 kilometers an hour. Find the induced current in the circuit. If, let's say, find the induced current in the circuit, if at the end of the track, we connected a light bulb with a resistance R of 10 ohms. That's a practical example. Okay, so we do have the velocity of the train, 40 kilometers an hour. We do have the distance between the rails, which is 2 meters. We do have the resistance of the light bulb, right, which is 10 ohms. And then we need to find out the magnitude of the magnetic field. And the magnitude of the magnetic field we can find out in the internet. By the way, the unit of magnetic field is the Tesla, right? Here you go. Let's take a look a magnetic field intensity at the South Pole, nearby the South Pole, at the North magnetic pole of the Earth. Let's see. Yeah, here you go. Nanotesla is very okay. 60,000. Okay. The magnetic field intensity of the Earth's north magnetic pole is approximately 60,000 to 70,000 nanotesla, which is 0.6 to 0.7 Gauss. Let's use 60,000 nanotesla. So 60,000 nanotesla is 60 microtesla. Microtesla. Yeah, 60 microtesla. Okay. So the magnetic field of the Earth change at every, depending where you are on the Earth, the magnetic field intensity is going to change. Not just the intensity, but the direction as well, okay? So let's see if we can build a circuit just by moving. Here you go. Here's the magnetic field, right? If that's the North Pole, so this should be the South magnetic pole, which should be nearby the North geographic pole. Antarctica should be here, right? If that's the South Pole. And let's see where I can get that now. This map here that I want. Can I zoom in? That's an important piece of information for whoever fly airplanes. Let's see here. It used to be important, but now it's no longer important because nowadays we have very reliable GPSs, right? At the time that we didn't have inexpensive GPSs, we had to rely on the magnetic compass to fly our airplane, for instance. And here are the intensity of the magnetic field, okay, 50,000, 45,000 ohms. Yeah, 65,000 right in here. They don't have, they have only at the latitude 80 degrees south, right? Only up to 80 degrees south. But the intensity of the magnetic field changes depending where you are on the Earth's surface. And what you see right in here are the lines of same magnetic field. Here is 50,000, should be nanotesla. Here is 55,000, here is 60,000, 65,000, and so on. They don't have exactly at the North Pole because we have only up to latitude of 80 degrees south and 80 degrees north, right? So let's use that value that I mentioned, 60,000 nanotesla. We can do the math. 60,000 nanotesla is 60 microtesla. Microtesla symbol. Yeah, like that. Like that. And I'm using 10 ohms. Let's put 10 ohms here. Let's see if we get a large current or not. Almost time for our break, right? Let's get some spreadsheets here to calculate our see after should be this one. Let's see if it's this one here. Yeah, that's the one, right? P07. Here you go. I'm gonna make a table. V, you gotta put everything in meters per second. B, you gotta put it in Tesla. L, you gotta put that in meters. What else? VBL, oh, the resistance. And we put it in ohms. Symbol. Here you go. I said 40 kilometers per hour, right? 40 kilometers per hour is 4,000 meters divided by 3,600 seconds. If you want to change to meters per second, right? 11 meters per second. Tesla, I said that we're going to use 60 microtesla. 60 microtesla is 60 e to minus 6. We use 2 meters, and we are using here 10 ohms. The induced current is going to be VBL B L divided by R. Let's see if the current is strong enough. Yeah, it's a current that we can measure with my multimeter, right? It's a little bit less than 1 milli. It's a tenth of a milliampere. 1/10 of a milliampere. You can measure that. Approximately 0.133 milliampere. That's the magnitude of the induced current that would be able to generate if we build this railroad there in the North Pole. If we build this railroad there in the North Pole and put a train to run there. And why did I choose the North Magnetic Pole? I chose the North Magnetic Pole because the magnetic field is the most intense there, like you saw in that drawing, right? Around 60 micro Tesla. That's the example that I want to do. This is an example of a motional electromagnetic force, motional EMF, electromagnetic force, that's right. And what we can do right now, any questions about that? Okay, so we can take our break now. Break, it is 10:45 oh, 10:45 a.m. to 11 a.m. Okay, and I see you in 15 minutes. Tá a aula. We are back here. Okay, so that's just a substituting above, right? Substituting the numeric results above, we get we get 0.1133, let's see, 0.133 milliamperes, which is, it's not very large current, but it can be measured. Yeah, 0.133 milliamperes. Current in our regular circuit is around up to 100 milliamps, 10 milliamps, 100 milliamps. Okay, that's the current that they should expect in regular electronic circuits, not more than 100 milliamps. So this fancy railroad at this speed would generate that much current. Okay, if you are going to increase the speed of our train, then we can do that too. Let's see, if we double the speed, right? If we double the speed of the train, the current would increase a little bit more, would double. The current would double as well because it's directly proportional to the velocity. If we increase the area too, right? If we double from 2 meters to 4 meters, and then the rail will be much wider, we also would double the current. We also would double the current and so on. Okay. And that's what we have for this example. Now what we're going to do, we're going to talk about I want to talk about the generator, but let's get here the chapters first, right? We already covered the magnetic flux too, right? It's just the magnetic field times the area. So let's update the material that we have covered so far in the chapter. Magnetic flux. We covered the Faraday's law as well. We covered the Lenz's law too, man. We covered everything, almost everything. Okay. And magnetic flux. Let's go here. Close. I want this one here. What happened here? No, it's not what I don't want. That's magnetic induction. That's motional EMF. Okay. Here he did a similar example that I did with different numeric values. And here's another example of motional EMF. You can get your rod sliding according to due to the gravitational force, right? two rails, two vertical rails. You clamp this rod in those two rails and let it move according to the force of gravity. You also connect the resistor right in here, making a circuit. Okay. Magnetic flux. Okay. And we cover magnetic flux as well. I did a problem similar to this one, right? And general expression for the magnetic flux, here you go. Phi in this case is the normal of the plane of the circuit, is the angle between the normal of the plane of the circuit and the magnetic field. So here's the surface of the field of the circuit, right? And here's the magnetic field. Here's the area vector. It's the same equation that I showed to you for the magnetic flux. Here's the coil. So here you go, the plane of the coil is perpendicular to the magnetic field. Consequently, the magnetic flux is greatest for this orientation. But when the coil makes an angle, the magnetic flux decreases, just like we had for the electric flux, right? And when the plane of the circuit coincides with the direction of the magnetic field, the magnetic flux is zero. The magnetic flux is zero, okay? Here we go. Lines of magnetic field vector. Faraday's law of electromagnetic induction. Here you go. The same equation that I provided you. Delta phi over delta t. And you can either calculate the induced current or you can calculate the induced electromotive force or the induced voltage. And now that's the example that I want to cover with you. The electromotive force induced in a rotating coil. And that's the very principle of the generator, of the electrical generator. Very important device, okay? It's because of this device that you have electricity all over our places, our houses. And there is a very nice, link that I want you to take a look. Okay, simulation of a generator. The electrical generator. Electrical generator. Here you go. Simulation of a generator. This is the Walter Fender website. We can go there. He has several interesting. Here you go. That's a simulation. The generator is very similar to the electric motor. If you learned about the electric motor, you will be able to understand how the generator works as well. One is exactly the opposite of the other. If you remember how the electric motor works, right? Let me slow down here. Let's go back to the electric motor that we saw before. And just to remind you how the electric motor works, and then we're going to compare to the generator. One is exactly the opposite of the other. Mechanics, oscillation, electrodynamics, electric motor, magnetic field, Ohm's law. Let's see. Lorentz force. Yeah, that's the one. Direct current electrical motor. Right in here. Both of them have a loop, right? Both of them have a loop. I'm going to copy that and paste there in my notes so you can have them. And I'm going to do the same with the other one. So you watch them side by side. Compare the illustration side by side. Light capture. I didn't capture anything, did it? Okay, let's try it again. Ah, what a shame. This. I'm gonna copy. Okay, electric motor. Insert table. Here we go. I'll put my electric motor here. I don't need the whole thing. Let me get just part of it. Go. Here we go. Yeah, electric motor. Electric motor, electric generator. Electric generator. Let's generator right in here. The elements are the same. Okay, so let's take a look. Electric generator. So here what we have the loop, right? Here we have a loop too. We have a bar magnet with a magnetic field, bar magnet with a magnetic field. The only difference, what's the only difference here? In the place of here we have a battery, right? In the electric motor, we need a battery and a circuit subjected to a magnetic field to get the thing moving, to get the thing rotating. So we have an input of electrical energy, and the output is the mechanical motion. Here is the opposite. Okay, here we input mechanical motion. So do you see this handle here? This handle is for us to pump it, to rotate it manually, right? And when we rotate this loop in the magnetic field, we induce a current in the circuit. The red arrows are the direction of the current. Is the direction of the current right in here. And then what else do we have here? We have a voltmeter. The voltmeter substitute the battery on the other side. This voltmeter is right in here to keep track of the variation of the voltage. And that's the type of voltage that we end up whenever we rotate the circuit with uniform angular velocity. That's what we get. We get this type of variation of the voltage. This type of voltage has a name. It's called AC voltage or AC current too. AC stands for alternate current. Okay, so two devices that are very similar. Two devices that are very similar. The electric motor and the electric generator. They're similar in the sense that the one is the opposite of the other. Similar in the sense that they use almost the same devices, right? Almost the same devices. But work in the opposite way. The electric motor and the electric generator. For the electric motor. Okay. Loop subjected to a magnetic field, right? Electric generator. Also, we have a loop subjected to a magnetic field. Então, then what else? Input is an electric current, electric DC current. Okay, or electric energy. The input here, is mechanical motion. Uniform rotational motion. Constant, input is, let's see, rotational motion, mechanical rotational motion with a constant angular velocity, Okay? Output. What's the output here? Output is mechanical motion, rotational motion. Here, the output is current and voltage that varies sinusoidally with time. That with a varying here with a varying angular velocity. Okay, so those, are the two types of devices. In a way, they're similar to each other. Okay, and we can even come up with a table to compare them. I think a table is better. Let's see, insert 1, 2, 3, 1. Let's see here, electric motor. Let's see, motor, generator. see here how we're going to do here. Device one. Device one. Loop. Current loop. Conducting loop. Conducting loop. Conducting loop. Right? Device two. Let's see, bar magnet. It's not a bar magnet. Horseshoe magnet, right? Horseshoe magnet. Horseshoe magnet. We also have a horseshoe magnet here. Device three. Device three is going to be battery. What replaced the battery in the generator is the voltmeter, ammeter. What else? Here you got the ammeter, right? Both of those. Let's see here. What else we can device four. For the electric motor, we have a commutator to change the direction of the current and make sure that the loop keep on rotating. Okay. And here, the device four is not a commutator. It's something else. It's the handle. To rotate circuit. Okay. Handle to rotate circuit. What else? We're done, right? With the devices, we're done. There's no more device here that we have to worry about. Input. DC current. DC electric current. Input is for the generator is rotation with constant angular velocity. Okay? Velocity of the handle, right? Like that. If here we have constant angular velocity, here we have a constant electric current. And the output is, what's the output? Varying angular velocity. Angular velocity. So here we can say electric input. The input is electric energy. Here, the input is mechanical energy. Varying angular velocity, and here is going to be mechanical energy. And the output, varying voltage / current. This type of current, let's put here sinusoidal. Sinusoidal voltage current. This type of voltage and current, we call it AC current. AC current. AC or alternate current, right? DC is a DC. Here we have DC. Here we have AC, right? DC electric current is direct current. output, electrical energy, mechanical energy, electrical energy. Here you go. Let me make it. Right. Organize my table here in a better way. Do you see the difference between those devices, right? Like I said, if you understand one device, it's not going to be difficult for you to understand the other device. Let's take a look. Horseshoe magnet. I'm gonna walk you through. Here you go. That's the horseshoe magnet, right? That's exactly what they have in there. We form a uniform magnetic field between those two poles of the horseshoe magnet. Sort of magnetic field, right? Here another horseshoe magnet. Okay, here you go. Another horseshoe magnet, and so on. So let me walk you through again. I'm going to go very quickly about the, let's see here, the generator. And then we want the direct current electric motor. Here you go. The motor here, how it works, right? It works according to Lorentz force law, the magnetic force law. We pass a current through this loop. When we pass a current through this loop and subject the loop to a magnetic field, there will be a magnetic force acting in the loop, and the loop is going to rotate. That's the direction of the force that you see right here, the black arrows. Okay, Lorentz force. I'm going to turn it off. Okay, here you go. See, I turned it off. Turning back. The black arrows is the Lorentz force. And this Lorentz force produces a torque in this loop. That's the principle of the electric motor. In the case of the generator, here you go, the black arrows in this case is the direction of movement, okay? The direction of movement. We do have an induced current, which is in red. Here's the induced current. Okay, and then this induced current changes direction as we rotate the whole circuit. What exactly is happening here, right? What exactly is happening here? Well, we are using Faraday's law of electromagnetic induction. At this point, let's see here if I can stop. I cannot pause it. Oh yeah, I can pause it here. Okay, so let's pause it exactly when the circuit has maximum. The circuit right now has maximum magnetic flux, right? Because the plane of the circuit is perpendicular to the magnetic flux. If the plane of the circuit is perpendicular to the magnetic field, not flux, but field, it means that the area vector is going to be either parallel or anti-parallel to the magnetic field, okay? So at this very moment, the magnetic flux is maximum. Because the magnetic flux is maximum, from here on, the magnetic flux must decrease, right? Here you go, I'm going to resume the motion. Here you go. Magnetic flux is decreasing until it reaches this point here. At this very point, the magnetic flux is going to be almost zero. It's not exactly aligned, right? Let me change here the rotation so I can Oh yeah, now it's aligned. That's nice. Exactly. Right now at this point, the magnetic flux is zero. Okay. If I resume the motion, now remember there's someone cranking this device right in here, making the loop rotate. What's going to happen from now on? From now on, the magnetic flux is increasing. The magnetic field is not increasing. The magnetic field stays the same. What is increasing is the magnetic flux up to this point. At this very point, the magnetic flux is maximum. And because the magnetic flux reached a maximum value, now it can only go down, right? So resume. Now the magnetic flux is decreasing, right? Until it reaches zero. Because the magnetic flux is changing as time goes by, you must have an induced current in the circuit. So watch the direction of the current right in here in this loop, right? So let's watch. Whoa, that now is increasing, right? The magnetic flux is increasing. Current is flowing in one direction. Magnetic flux, oh, see that? Now magnetic flux is decreasing. That's why the current switch sides. You can see that the direction of motion, the black arrow, right, is not completely aligned with the magnetic field. That's because we just passed the point of maximum flux. The moment we pass the point of maximum magnetic flux, the current switches direction. And if you manage to keep this guy rotating with uniform circular motion, you generate exactly an alternate current that has a sinusoidal behavior, sinusoidal or cosinusoidal behavior. And watch this voltmeter, right? Here you go. The voltage keep on increasing. See that? Keep on increasing. And now it looks like it's already decreasing. Yeah, it's already decreasing. Watch this. Let's increase the rotation so you can increase the voltage. We can hardly see anything here, right? Here you go. Now you can see the voltage is oscillating back and forth. A minimum value right in here, pass through zero, maximum value, minimum value. Let's see if I can pause exactly at zero. Exactly at zero is where the magnetic flux is maximum. Okay, and so on. Let's write that down. How it works. Let's see if I can. I'm gonna put it very slow too. Let's see here. I'm gonna copy those pictures in our. When the black vector, okay, the black vector is almost aligned up with the magnetic field. See that? At this very moment, the magnetic flux is maximum. Okay, I'm gonna copy this guy here. How the electric generator works. How the generator works. One is starting at maximum magnetic flux. Okay, maximum magnetic flux. Start at maximum magnetic flux. The voltage, the induced voltage is zero. The induced voltage is zero. Maximum magnetic. Why the induced voltage is zero? Because at maximum magnetic flux, right? The magnetic flux is changing from from a positive slope, let's say from a positive slope to a negative slope. When we have this change from positive slope to a negative slope in time, right? Variation in time, it means that the magnetic flux, the change in magnetic flux at maximum is going to be zero. Maximum magnetic flux, induced voltage is zero. Induced voltage is zero. Induced voltage is zero because, delta of, let's see here. Delta phi, delta t, because delta phi, delta t at this point, because at this point is zero, okay? It was increasing, right? Just before it reached the peak, the delta phi, delta t was increasing. Just after it reached the peak, the delta phi, delta t is decreasing. What does it mean? It means that the delta phi, delta t was zero at that very moment, okay? Starting at the maximum. And let's see, step two. Resume. Between, here you go, between maximum magnetic flux, B flux, right? Let's put it this way. B flux and zero B flux, comma. Okay. Delta phi, delta t decreases. The flux decreases. Consequently, the voltage turns negative. Okay. Consequently, the voltage turns negative. When B flux reaches zero, delta phi, delta t delta phi, delta t has maximum negative variation, which provides a negative voltage of maximum magnitude. Like that. Let's take a look. Here you go. Let's put it to rotate. You're going to see that this needle, let me go, gosh, should be right in here. Oh, a little bit more, right in here. You can see maximum deflection of the needle towards the negative values, right? Let's put maximum deflection of the needle. Maximum provides a maximum deflection of the voltage needle, right? Voltage needle towards negative values like that. And I'm going to copy and paste what you see there, okay? Now, what I'm gonna do? What's gonna happen? Now the magnetic flux is going to increase, right? Magnetic flux increasing between 0 B flux, 0 B flux, and maximum B flux. Now, wait a minute. Let's take a look here. Between B flux reaches 0. Yeah, between 0 B flux, right? 0 B flux and maximum B flux increases. Consequently, the voltage turns positive. Going back here, right? Now, when we reach this point, we have maximum magnetic flux. Maximum B flux. Maximum B flux. The induced voltage is 0. And the cycle repeats itself. Now we are back to this point, okay? And we can go ahead and copy maximum flux, current going one direction, maximum B flux, current induced. Get one more student here. Here we go. Maximum B flux, current induced is 0. Current induced is 0. Current slash voltage induced is 0. This one here. In between, here you go. Resume right here. Between maximum B flux and 0 B flux, right? Between maximum B flux and 0 B flux, B flux decreases. This one here. Current flows, let's say, in the positive direction. Now, let's see here. Resume right here. B flux equal to 0. B flex equal to 0. What we have maximum voltage. Maximum voltage. This point right here. So we start right in here, pass through here, we are here, right? Now the voltage will decrease. Okay. Now here go. Around here. Let's go a little bit more. Here you go. A little bit more. Now the B flux is increasing again. B flux increasing. Right? So here you go. B flux increasing again. Let's take a look at the direction of the current flow, right? Here you go. The current during this instant of time, the current is flowing from here, right? To here, the current is flowing in the same direction. It didn't invert the direction yet, right? Next, when the B flux is maximum, let's get that here. Maximum B flux, voltage is 0, and current inverts the direction. Let's see here. At maximum B flux, induced current slash voltage is 0. Current is about to change direction right here. Just pass, so it's negative. So let's see. Do we have the full cycle yet? We started right here with the voltage increasing, right? Now we are right in here with the voltage increasing in the negative direction. So we start here, we are here. We got 1, 2, 3, 4, 5, right? 5 illustration. One is not the full cycle yet. 1, 2, 3, 4, 5. Not the full cycle yet. We need how much more? We need if you want the full cycle, we need 1, 2, 3, 4. 4 more points, 4 more drawings, right? And you can do that by yourself. Now that you have, I want you to closely study this situation so you can understand how the electric generator works, okay? Any questions about that? You have the link for the generator. You can do exactly what I'm doing here. Copy the situation, right? Maximum, you copy the situation at maximum flux in between maximum and zero, at zero flux, and the other side as well, just like I am doing here. And that's how you learn about how the generator works. And in the process, the current has to switch direction. And that's exactly this type of current, okay? This type of AC current is exactly the current we get from the outlet at home. Alternate current, alternate current. Alternate, it is alternate A/AC. It is alternate because it keeps on changing direction of flow. Okay, keep on changing direction of flow. That's why it's alternate. The other current, this type of current is produced by a generator, right? This type of current is produced by a generator. The other current is the direct current produced by a battery. The other current, the direct current, DC, produced by a battery. This current flows in a single direction. This current flows in a single direction and is constant. Okay, AC/DC. So it is now 11:53 a.m. Let's take another break. Let's see, to 12:08 p.m., right? Yeah, 12:08 p.m. So let's have a break and I'll see you in 15 minutes. Bye. Okay, we're back here. And let's continue the treatment here of the generator. Going back to our equation here. Here you go. Faraday's law, right? We're going to use this one. Let's use just one coil for our generator. And the nice thing about those circuits is that if you want to increase the voltage, all you have to do is to increase the number of coils, right? If you have 10 coils, you can come up with an induced voltage that's 10 times more, okay? And recall, right, that what is the magnetic flux, right? The equation for the magnetic flux is this one right here. Okay, is the magnetic field that's parallel to the area vector. And this angle between the magnetic field and the area vector, I call it the angle theta. And as you saw before, generators that we have out there, they produce a uniform rotation. So this angle theta here can be written in terms of an angular velocity times instant of time. Make sense? Okay? That's why, and that's why you end up getting that voltage that varies sinusoidally, because we are producing a uniform rotation. for the coil. That go. Okay, that now one thing that's very important, right? Okay, if the flux change in the cosine fashion, okay, when we put this guy right in here in this equation, right? What do we get? We're gonna get something interesting, okay? Here you go. The BA can be taken out of this delta symbol, so it is just like differentiating, okay? We don't cover differentiation in this course, but I'm gonna tell you what happens when we have this change of cosine of omega t with respect to time. What we end up having is this term here is going to be a function of sine, but it's not just a function of sine, of the sine function, but it's also going to be a function of minus this sine function. Let's see here. Get this one. And I want to just to memorize that, okay? Omega is going to be something like that. And this negative sign cancel out with the other negative sign, okay? If you have taken differential calculus, you'd know that. If you haven't taken differential calculus, I need you to memorize this result, okay? This delta cosine of omega t delta t is in reality omega, here you go, minus omega sine of omega t, okay? That's going to be my induced voltage, the voltage that you saw in there. And now also, my current, the induced current, is going to be just remember the induced current is going to be oops, oh gosh. The induced voltage divided by R, right? And induced that divided by R, like that. And here is the very definition of an alternate current or an alternate voltage. Is either a sinusoidal function or a cosinusoidal function of time. So that is how we create an alternate current. Alternate current by rotating a closed loop circuit in a uniform magnetic field. It's one of the most important devices that we have out there. Okay, is this generator, which is nothing but the generator. This rotation can be accomplished in many ways. Can be accomplished in many ways, right? By a human hand, You can also couple this thing to a treadmill, couple this circuit to a treadmill, for instance, treadmill, and walk over and walk over it. Okay, can be coupled to the wheel of a bicycle, right? The wheel of a bicycle. We used to have those in my time. We would have a generator installed in the wheel of my bicycle, and every time that I want to turn on my lights of the bicycle, I just pedal, okay, and the wheel of the bicycle would turn the generator, and I would produce electricity. Nowadays we don't do that. Nowadays we just install a battery in there. Another way to do that is with an internal combustion engine, right? Combustion energy engine. That's what we call a thermoelectric generator. Thermoelectric generator can be diesel or can be gasoline. Thermo. Let's see, thermoelectric generator. Here you go. Several ways of producing electricity. Can be also hydroelectric power plant, hydroelectric power plant, which uses the potential energy of the water to rotate a turbine. Okay. Several ways. Here, I'm going to list them all. One, by human hand. Couple the circuit to a treadmill, right? You walk over the treadmill and you rotate the circuit. What else? Couple the circuit to the wheel of a bicycle. So there are all sorts of ways that we can create a generator with an internal combustion engine. Hydroelectric power plants. Which uses the potential energy to rotate, right? To rotate a turbine coupled to a circuit, etc. Now, because now our current is changing in time, we adopt a different notation for the current of the circuit. We, instead of writing down as a capital I induced, okay, from now on, here you go. From now on, every AC current or voltage is written in lowercase, okay? So in a DC circuit, right? We usually, and that's adopt the letter I capitalized, right? As the current. In an AC circuit, you usually adopt the lowercase I for the current. So not what I want, this one that I want here. For this AC circuit, the current is going to be is going to be indicated by the lowercase I, which is proportional to sine of omega t. Okay. So let's copy here chapter 22 so far. We did this one, motional EMF, magnetic flux. Lenz's law, we covered that as well. We are skipping this chapter here, and we covered electric generator. Okay, we're almost over with that. And now we have two more sections to cover. Now we're going to talk about mutual inductance and self-inductance. Remember that I told you that we're going to cover, we already covered the capacitor and resistor, right? These two devices have can be characterized by a capacitance and resistance, right? Capacitance is charge over voltage, resistance is voltage over current. But I also told you that there are three other important devices, right? The inductor, the transistor, and the diode. All these 5 devices is everything that you need to build any electric or electronic circuit. That's all you need. And that's where we start talking about the inductor. Okay. I'm going to here write those equations right in here that you have. The two above equations can be here written as, V equal to Q over C, right? V equal to RI. We are talking about the Ohm's law here. And now recall what we have for Faraday's law, right? We also have a relation for the V, right? The induced voltage or the induced electromotive force. The induced voltage or the induced electromotive force is what you saw before. We have a negative sign, we have the number of loops, and then we have this relationship that you see right in here. We're going to elaborate that a little bit more. Let's continue writing. You know that the flux is going to be given by the magnetic field times the area through the magnetic field is flowing. But we also know that the magnetic field is always proportional to the current, right? Remember I told you? I'm gonna do for the special case of a solenoid, right? The magnetic field is given by, remember we derived there in the classroom, in the lecture, here you go, is a uniform magnetic field for the solenoid. We're going to do for the solenoid, but whatever we do here also applies to the other devices, right? The magnetic field. Okay, so no area here. It's going to be mu naught and the current. when we substitute that in this equation, we get something like that. Induced let's see here. And oh yeah, here you go. So what am I doing here is the following, right? It's better if I illustrate that for you. So let's see here. Let me get illustrations. Electromagnetic induction. Right here. Okay, I show those, right? What I want to show you is the following. Go. Yeah, here's an illustration of my generator. I showed that to you as well. Yeah, okay, here you go. That's where I'm getting. I want to get. Here you go. Consider a solenoid of length L and turn connect to a generator, right? That's the symbol of the generator. Keep that in mind. We have a generator that's producing a current through these solenoids. Okay? Have a generator that's producing a current through the solenoids. So this solenoid is now, think about the current flowing back and forth in the solenoid. It has also a magnetic field inside it that is determined, its direction is determined by the direction of the current. The direction of magnetic field depends on the direction of the current. Okay, if the current here is from the left to the right, okay, the left to the right, the field is going to be to the left. But if the current is flowing on the other direction, go. See, if the current is flowing in this direction here, okay, you do the right hand rule, and the magnetic field is going to point on to the right side, to the right side. Okay, here you go. But and what else? What else do we have? Because this thing is a generator, the current is increasing and decreasing as time goes by. Right here you go, at a given instant of time of maximum current, we have maximum magnetic field inside the solenoid. As the current starts to decrease, the magnetic field decreases as well. Eventually, it's going to come to the point where the current is going to be zero, and the magnetic field will have to be zero too. But soon afterwards, right? Here you go, smaller magnetic field. Soon afterwards, the electric current is going to change direction, and so will the magnetic field. We'll have this type of cycle, okay? Whenever my solenoid is connected to a generator. Let's do that again. Let's take a look. Here you go. Here you go. Solenoid connected to a generator. Right? In this specific case, the current is flowing in this direction. point of maximum current. Current decreases, the magnetic field generated by this current is going to decrease as well. It's going to decrease, until it reaches zero, and then after reaching zero, it changes direction, and the magnetic field is going to change direction as well. Okay? That what you should expect for the magnetic field of a solenoid connected to a generator. Okay? So let's get to our notes now. Get back to our notes. For the special case of a solenoid connected, right, to a generator, comma, its magnetic field is given by, it's going to be given by this relationship that you see right in here. Because the solenoid is connected to a generator, the current through the solenoid is not the induced current, but the regular current is going to be a function of time. And because the current is a source of magnetic field, the magnetic field will also be a function of time. Okay? Will also be a function of time. Now, this, like I said, there is no induced current here so far, okay? But now, think in terms of some different type of device. Okay, we have 20 more minutes to go. I think we can cover that. Here I have my regular solenoid connected to a generator, and I come by and say, look, I'm going to connect this primary solenoid. I call it primary because it is the source of the power, because it has a generator connected to it. I'm going to connect my primary solenoid to a secondary solenoid that has no power whatsoever. One solenoid has a length L. The primary solenoid has a length L. The secondary solenoid has a length L prime. Okay? This primary solenoid has any turns, and the secondary solenoid, we're going to need that, has any n prime turns. When we have a situation like that, okay, you already know that this primary solenoid will induce a current on the secondary solenoid, right? So here you go. I'm going to copy this figure here. This one right in here. And I'm going to paste there in the notes. Okay, for the special case of solenoid connected to a generator, its magnetic field is given by, okay, like that. Solenoid connected to a generator. Solenoid of n turns connected a generator. Now, we introduce a second solenoid coaxially with the first one. The first solenoid we call it the primary solenoid, the primary one, and the second solenoid, the secondary one. And it's going to look like this other picture that you saw right here. Copy. And by the way, I should make it lowercase l, okay? Otherwise, I'm not gonna use uppercase for a very good reason. Lowercase l. Let me just, and there is a reason for that. Yeah. Now, we have what, 15 more minutes to go, right? Bear with me while we cover that. And now that we introduced a second solenoid, which also has a closed circuit, right? You see the wires here, but there is no source whatsoever. There is no power source for the secondary solenoid. However, because it's subjected to the magnetic field of the primary solenoid, a magnetic field that changes in time, we are going to have a current induced in the second solenoid, okay? So here you go. Because the second solenoid is subjected to a changing B field from the primary solenoid, comma, because the secondary solenoid, oh gosh, secondary solenoid is subjected to a changing B field provenient from this primary, provenient from the primary one, comma, there will be a current induced in the secondary solenoid. Okay? So think about that. Think about that. We have a changing magnetic field here inside the solenoid. And by the way, and there will be an induced current in the secondary solenoid. And then what we can write down that the induced voltage, here you go. Let's write that here. The induced voltage right here. Right? It was going to be the magnetic flux through the secondary solenoid. So instead of N, we are going to have N prime here. Okay, continuing here the math, right? The magnetic flux is going to be the magnetic field of the primary solenoid times the area of the secondary solenoid, which I'm calling A prime. But because we are talking about a solenoid, the magnetic field of the solenoid is going to be given by this relationship that you see right here, where n, lowercase n, is going to be the number of turns of the primary solenoid divided by the length of the primary solenoid, like that. Okay. We can go further. Here you go. I can take all that stuff from here, put outside, and because it's all nothing of that is changing in time. Okay. And that's going to be the area. A prime is don't forget, is the area of the secondary solenoid. And then we have this term here that is a change in the current divided by change of time. Okay? Change in current divided by the change of time. That's going to be the relationship for the induced voltage in the secondary solenoid. Okay? There is something called, self-inductance and mutual inductance. Okay? So what's happening here? Mutual inductance is when one solenoid induces a current in a second solenoid. That's what it is, okay? There's something that we call there is something, we're gonna put mutual inductance first because we're dealing with that first, okay? There's something called mutual inductance and self-inductance. Mutual inductance is when one device induces a voltage slash current in another one, okay? In another one, which is exactly the illustrated example above, okay? Self-inductance is when the device induces a voltage current. The device induces a voltage current in itself. Okay. So let's talk about mutual inductance first. Okay. So it has a parallel very close to that of the resistor and capacitor, right? Let's see, where's that? Okay, that's what I want. Look what's happening here, folks. We have 6 more minutes to go, right? I want to take advantage of that. Notice that for a capacitor, we have this relationship between the voltage, the charge, and the capacitance, right? For the resistance, we also have a similar relationship. The resistance, the change of charge, right, with respect to time, which is nothing but the current. Let me hear right. For the capacitor, for the resistor, which by the way, Ri, and now we have something else that looks very familiar to what we are getting here, okay? For an inductor. And now for an inductor, 1, 2, 3. And now for an inductor. Here you go. This whole thing that we see right in here, we give it a name. We call it mutual inductance. Okay? And he write it as M. And there is more. There is more. Look what's happening here. Here we have Q. Here we have delta Q over delta T. And here we have delta I over delta T. Look how the whole thing is progressing. It is as though as we are increasing, right? The change in the charge, right? Here's the charge with no change. Here's a change of charge in time. And here is a twice the change of charge in time. Do you see what's happening here? We have V on the left side for all those three devices. We have something that relates to the charge of the device at different powers. And then we have something else that defines some characteristic of the device itself, which is a function of the geometric parameters of it, right? The capacitance is a function of the geometric parameter of the capacitor. The resistance is a function of the geometric parameters of the resistor. And the mutual inductance is also a function of the geometric parameters of my inductor. We have an area here, we have a length here, and then we have the number of turns that you get, okay? So let's put them side by side, down one after another, right? Without any distances. Here you go. This is a very nice mnemonic that you can use to memorize how the voltage relates to the device. Okay, and don't forget this one is mutual inductance. And then we have something similar for the self-inductance, okay? It's 12:48 now. I think it's a good point to stop right now. Do you have any questions? So note that there is a logical progression, mathematically speaking, among the three different devices, okay? Next time, we will do the same. Today, we did that for this mutual inductance. Come on, next time, we'll repeat that. We will repeat the above for the self-inductance. Okay? So, and then I'll tell you too that there is a unit behind that too, okay? And I'll fill that up next time. If you have any questions, I'll be here another hour for the office hours, okay? If you don't, I'll see you on Wednesday when we're gonna have our second exam. I see you on Wednesday.
Thank you.
Welcome.
Hi, Professor.
Hi.
Remember I emailed you about the question about my lab?
Uh-huh. Okay, you sent me an email about the lab, is that right?
Yeah.
Let me pause here.